Hello, this is Miraj Patel, and today we're going to be talking about limiting reactants and percent yield, and these two PowerPoints will be the last part of Unit 9, which is all about stoichiometry and calculating amounts in chemical reactions. And so, before we start talking about limiting reactants, let's just look at the scenario. So here we have one completed race car, and notice how the race car, each one has four wheels, one body, which is a triangle, one engine, which is this little gray rectangle, and three pistons, which is represented by these small little rectangles. And then we have all these parts. And so the question is, how many cars can we make from all these parts? And so we start looking. We notice we have three bodies, so we can make three cars with that much. But we only have two engines here. So there's only two engines available, so these two engines end up limiting how many cars we can make. And so we have enough wheels to make two cars, we have enough bodies, we have enough little pistons, so the two engines is what's limiting us. And so we end up making two cars just like this, and after that we end up with some excess stuff. So we end up with one extra body, one wheel, and several little pistons. And so in chemistry the same thing happens. And so in chemistry the amount of products, or in this case cars, created is limited by the amount of one reactant. So one thing, in this case it was the engines, limited the amount of cars we can make. And the same thing happens in chemistry, in chemical reactions. One of the reactants limits the amount of product, or stuff we make after the reaction. And so the limiting reactant is completely consumed, so this reactant is used up completely, and it determines the amount of product formed. Then we have excess reactant, or the reactants that are left over. So in this case these would represent the excess reactants, and then these two engines will represent the limiting reactants. These are completely used up, and then these are all left over. And so now we're gonna look at a real chemistry problem, not just a car scenario. Sorry for you all those car lovers out there. And so here we have a diagram of these molecules. So we have three N2 molecules, and we have three H2 molecules. And then we form NH3, so we need one nitrogen and three hydrogens for each one. So if we only have 6 hydrogen molecules total, because 3 times 2 is 6, we can only make 2 of these NH3 molecules. But then we have leftover nitrogen here, and no, we have 2 of these molecules left over. And so in this case, the nitrogen is the excess or leftover reactant, because we still have some nitrogen left that can still be used. And the hydrogen is limiting because it runs out and limits this whole reaction. So pretty much we just talked about how limiting reactants work. So this limiting reactant limits this whole reaction. So even though there's 3 moles of nitrogen here, right here, is enough to make 6 moles of NH3, but this hydrogen is used up only after making 2 moles of NH3. So the whole point is that limiting reactants limit other reactants, so that there's some excess. And so now we're going to determine limiting reactants, but this time we're going to use math, not just pictures. And so here we have a chemical equation, and we're asked which of the following is limiting this reaction. So we have 48.6 grams of Mg and 110 grams of HCl. And so how could you figure that out? How does a few grams tell us how much we can make? And so the part that we use to, or the way we use it to calculate limiting reactants, is we have to convert from each reactant to a mole of the same product. So we have to convert these reactants to moles of hydrogen or MgCl2, but in this case, we're just going to convert both of these to hydrogen. So we convert how much of this can make how much of hydrogen, and so we do it for both of them, and we compare the values. So we have this first set of conversions. We convert from magnesium to hydrogen, and so we first divide it by molar mass to find how many moles of magnesium there are. Again, whatever's on the top goes on the bottom of the next fraction, so we put grams on the bottom, and we put 1 mole because molar mass. Then we convert from moles of Mg to moles of hydrogen using mole to mole conversion, or mole to mole ratio, which is calculated from these coefficients right here, 1 and 1. And again, whatever's on the top of the first fraction goes on the bottom of the next. So we cancel out moles and we're left with moles of hydrogen. We multiply all the tops, so 48.6. And then we divide by 24.31 because all these ones don't do anything at all. And we get about 2 moles of hydrogen. Then we do the same thing with with the other reactant, HCl, and we convert to hydrogen. So we did the exact same thing, divide by molar mass, again, grams on the top, so grams goes on the bottom, 1 mole becomes molar mass. And then we convert from moles of HCl to moles of hydrogen using mole to mole ratio, which is calculated from the coefficients. And so moles of HCl, 2 moles of HCl from here, and 1 mole of hydrogen because there's 1 mole here. And so we multiply all the numerators and then divide by the product of the denominators, and if we do that, we get 1.51 moles of hydrogen produced from 110 grams of HCl. So after we do that, we look at which one makes less of the product. So out of this, from 48.6 grams of magnesium, we made 2 moles of hydrogen, but from this, we only made 1.5 moles, or 1.51. So this one definitely made less. So whichever product made, or reactants made less, is what's limiting. So in this case, we go back and see that HCl is limiting this reaction. And so we find out this is limiting, and then to find out the excess of magnesium, we convert from 110 grams of HCl to grams of magnesium, and then subtract the grams we calculate right here, we'll get, from the excess here. So here, now we're doing the last step. So we have 110 grams of HCl, use molar mass to convert to moles, like this. So we divide by grams because grams is on the top, so it goes on the bottom, 1 mole on the top. So we're left with moles of HCl. Convert from moles of HCl to moles of magnesium using mole to mole ratio, which is calculated from these 2 coefficients. So 2 moles goes on the bottom because moles of HCl cancel out. Then 1 mole is calculated from here. So now we're left with moles of magnesium. Then we go from moles of magnesium to grams by using molar mass. Moles of magnesium goes on the bottom, and so they cancel out, and it's 1 mole because molar mass. And then 24.31 grams of magnesium is calculated from the periodic table. And then after you multiply all the numerators and divide by the product of the denominators, we get that it's 36.7 grams of magnesium. And so after we have this much, we can subtract this from the moles of magnesium here to find how much is left over. So this is how much is used, and so we need to find out how much is left. So we just subtract. So we subtract 48.6 from what's consumed. And notice how when we subtract from HCl, we know that we use 110 because this is the limiting reactant. So remember, the limiting reactants are always used up, just like in the car scenario, that both the engines were used up, so we're left with no engines. This same thing. So we used up all the HCl, so we have no leftovers. But this one, we only use 36.7 grams. So we subtract this and we get 11.9 grams of Mg. And so this is how much is left over at the end of the reaction. And again, this is 0 because it's a limiting reactant. So remember, limiting reactants are always used up and will always have 0 leftovers. And then that's the excess because it's not limiting. And now we're going to determine the amount of product with the limiting reactant. So again, we do the same exact steps. So first we read the problem. So we're asked how many grams of CO2 can be formed from 2.7 moles of C2H4 and 6.3 moles of O2. So we have these moles and we use molar ratio because we're given moles and we want to convert to moles of CO2. So here's CO2. So we convert from moles of C2H4 to moles of CO2 first, then O2 to CO2. And so because moles of C2H4 is on the top, we put moles of C2H4 on the bottom. And so 1 mole of C2H4 and then 2 moles of CO2, which is calculated from these coefficients right here. And then we get 5.4 moles of CO2 if we have 2.7 moles of C2H4. Then we do it with O2, same exact thing. Moles of O2 goes on the bottom because it was on the top, so we have 3 moles of O2 and then 2 moles of CO2, which goes on the top. And so we multiply by 2, 6.3 times 2, and then divide by 3, and we get 4.2. And so if you remember, the one that produces the least amount of product is limiting. So this 6.3 grams of, or moles of O2 is limiting. So now we can convert from moles of CO2 to grams of CO2 because that's what it's asking. We need to find out how much grams is produced from this much CO2. So we convert this to grams by using the molar mass of CO2. So we calculate the molar mass of CO2 from the periodic table. And so we use 4.2 moles of CO2. Then we put 1 mole on the bottom because it's molar mass. So 1 mole goes on the bottom, so moles cancels out. And then we find the grams of CO2, grams in 1 mole of CO2, and it's about 44.101. And so we just multiply these two numbers, and we get a gram amount of 185 grams of CO2 produced. So pretty much we just figured out the limiting reactant just like we've been doing on the last step or power slide. And then once we found the limiting reactant, which produces less product, we use this to find out how many grams are produced of this product by using molar mass of CO2 to convert to grams of CO2 from moles of CO2. And so here's a quick quiz to see what you learned. How many grams of H2O can be formed from 64 grams of O2 and 3 moles of H2? So here we have these two amounts, and so we need to convert to O2 or grams of O2. So first we find out which one's limiting. So again, we convert from moles of oxygen, grams of oxygen to moles of oxygen, then moles of oxygen to moles of H2O. And so we divide by the molar mass first. Grams goes on the bottom because grams is on the top here. Then we put 1 mole on the top because it's molar mass. Then we convert from moles of oxygen to moles of hydrogen here. And so here we have 1 mole of oxygen, 1 mole of oxygen cancels out, and we're just left with H2O moles. And after multiplying all the numerators and dividing by the product of the denominators, we get 4 moles. Then we do the same thing with H2, but this time H2 is already in moles, so we just use mole to mole ratio from H2 to H2O to figure out how much moles of H2 we can produce. So we put H2 on the bottom because it's on the top here. Then we put moles of H2O on the top, and the mole ratio is 2 to 2, or pretty much 1. So if we multiply 3 times 2 and divide by 2, the 2's just multiplication of 2 and division of 2 just cancel out. So it's pretty much 3 times 1, and we get 3 moles. So after getting 3 moles, We find out which one's smaller, and 3 is definitely smaller, at least on Earth here. And so this is limiting, so this is what we're going to use to find out how many grams of O2 we have. So we multiply 3 times the molar mass of water, and moles goes on the bottom, so it cancels out, and we're left with grams, which is from the periodic table here. And we get about 54 grams of H2O. And so that is it. And so now we're going to be talking about percent composition. And so we're going to still be converting. So I'm sorry if you don't like math, but the good part is it's all simple. It's just multiplication. And so here, before we begin, we're going to talk about percents. So percents are pretty much calculated by dividing what we have out of the total. So in this one, what percent is 8 of 20? 8 is the little part of 20. So we do 8 divided by 20, and we just multiply by 100, so we get percent. Because otherwise, if we just did 8 divided by 20, we'd get a decimal. And then if we multiply by 100, we get a percent, because we just moved the decimal places 2 places. And then we get that 8 out of 20 is 40%. And so now we have a second one that's a little bit more related to chemistry. So if a reaction made 50 grams of product but was supposed to produce 75 grams, what is the percent produced? So again, percent is, think about it, percent is how much of the total was used or made. And so if we made 50 grams when we should have 75, we do 50 divided by 75 and get that 50 out of 75, if you just think about it, is just reduced to 2/3. Alright, and then we can just enter that in the calculator. So 50 divided by 75 times 100 is 66.666%, or you can just round it to 67%. So just think about just fractions and math. So pretty much when you're doing percents, divide the partial amount by the total. And then now we're going to bring it back to chemistry. So percent yield is amount of product recovered as a percent of the product intended. And so pretty much percent yield is how much out of how much we expected do we get. So if we calculated 10 grams and we only got 9, how much percent is 9 out of 10? So the formula for percent yield is right here. So is the actual yield divided by theoretical yield times 100. So what we actually got in real life is actual yield. What we calculated using these formulas times 100. And so again, here's the formula, and this is actually what the terms mean. So theoretical yield is the maximum amount of product that could be formed from the limiting reactant, and this is also known as calculated yield. So if it says calculated yield, it's the exact same thing as theoretical. So theoretical is what we calculate using these formulas and conversions. Then actual yield is what is produced in the laboratory. So what is actually produced in real life. So just think about, so if we actually did this experiment, how much did we actually get? And then again, here's the formula: actual yield, or what we got in real life, over what we calculated, times 100%. And so here's our first problem we're going to do together. So calcium carbonate found in seashells decomposes by heating, as shown in the reaction. So we have CaCO3, and then it decomposes into CaO and CO2. And so what is the theoretical yield of CaO if 24.8 grams of CaCO3 is decomposed? So we have this many grams of the reactant, and we need to find out how much CaO is produced. So again, we use all the stuff we learned from back earlier in this unit. So we convert from grams to moles, and this time this problem's pretty nice and all set up because it just gives you the molar mass. But if you had to calculate, we look at the periodic table, add up the calcium, multiply by the calcium's atomic mass. Same thing with everything else, carbon and oxygen. And we add them all up and we would get 100.09. So we divide by grams because grams is on the top, so grams cancels out, we're left with moles. Then we convert from moles of CaCO3 to moles of CaO right here. So it's 1 mole to 1 mole. So we put CaCO3 on the bottom because it's on the top, so we need to cancel out. Then we put 1 mole of CaCO on the top because that's its coefficient. And then we multiply by CaO's mass, atomic mass. And we calculate that from the periodic table. And so because we have moles on top, we put moles on the bottom. And then CaO's mass is 56.08. So we multiply all the numerators, divide by the product of the denominators, and we get 13.9 grams of CaO. So if we had this many grams of CaCO3, that means we should theoretically produce 13.9 grams of CaO. And so now we want to calculate percent yield. And so this time it gives us that what is the percent yield if we produce 13.1 grams of CaO is actually produced when we had 24.8 grams of CaCO3 is decomposed. So we just did this a second ago. So we calculated all this before, and this time it's asking for percent yield, so which is actual right here over what we calculated times 100%. So we do what the formula says. So we put actual over theoretical right here, which we calculated from the last slide. And then we multiply by 100%, and then we get 94.2%. And this is an important point to know, that percent yield is usually less than 100. And the important part is that percent yield, because we're in the real world, and in the real world maybe not all the particles might not react. So not everything might react, and that's why we get numbers usually smaller than 100%. So remember, percent yield is always usually less than 100, because maybe not all the particles reacted, or maybe the temperature affected the reaction, and so it reacted less. So it can only react up to 100%. So we can only get a reaction of completeness. We can't react more than what we have. So that's why reactions are usually less than 100, and they can only be 100. They cannot be anything greater than 100. So that's always important. So if it's ever more than 100, you did something wrong. So remember, reactions, the percent yield is always 100 or less than 100, and it can never be like 0. It can never. It can never be negative, nor it could be anything greater than 100%. And it's usually less because in the real world, all the particles might not react. So that's why we get stuff usually less than 100. So it's always important to think about it. So if you ever see anything more than 100%, that means you probably did something wrong and you have to check back your work. So that's a good part about percent yield. You have like a little check step. So if you know you're between 100 and 0, it should be correct. And so here's a quick quiz to see what you learned. So here, the theoretical yield is also called A, the percent yield, B, the actual yield, C, the calculated yield, or D, the experimental yield. So theoretical yield, if you remember, theoretical is sort of like what's calculated. So theoretical physics is all about what's being calculated. So theoretical yield is, remember that stuff we did with the math formula. And so if you think about it, we're just doing calculations. So theoretical yield is also known as the calculated yield because it has to do with all those math formulas, and that's what we calculated using formulas. And now here we have our last problem, pretty sure. And so what is the percent yield of CO2 if 14.6 grams of CO2 are recovered when we had 5 grams of C8H18 are combusted. So we're get asked to calculate percent yield, which is actual yield over theoretical times 100, and we're given we have an actual yield of 14.6 grams, and then we are given that we reacted, or we're gonna react 5 grams of C8H18 right here. And so now we have to calculate the theoretical yield, and luckily this problem's nice and gives us the molar mass, so we don't have to go calculate it. So here we set up our whole long conversion. So we start with 5 grams of this hydrocarbon. Then we move from, we use molar mass to convert from grams of this to moles. So we divide by grams because we start with grams. And then we start with the moles on the top. And then after we do that, divide. Grams cancels out, we're left with the moles. And now we convert from moles of C8H18 to moles of CO2, CO2. And we use the coefficient, so 2 goes on the bottom because moles of C8H18 goes on the bottom, because whatever's on the top goes on the bottom, and then we put 16 because that's where the CO2 goes, and now we're on moles of CO2, so that's good. Now we have to convert to grams of CO2, and so we put 1 mole on the bottom because we start with moles goes on the bottom. Then luckily it gives us that it's 44.01 grams per mole, so that goes on the top. And we just multiply all the numerators and divide by the product of the denominator. And so after that, we get a theoretical yield of 15.4 grams. And so just before we calculate this, it's always important when you're doing like math problems in any class, even in math class or chemistry, no matter what it is, always in the back of your head have an estimate of what it should be. So when you look at these answers, if we did 14.6 divided by 15.4, it must be close to 100% because 14.6 is pretty close to 15.4. It's only 0.8 off. So in the back of your head, you should be thinking that this answer should be close to 100 somewhat. And definitely, we just talked about how percent yield can never be over 100 because we can never get more than what we have or what we're expecting to have. So definitely not A, and no other answer is close to 100 as B. So, and in fact, if you did do this, the answer would be B. But just as a smart tip, just as test taking in general, always have an estimate. So when you do math, just have a ask yourself, does it make sense? And in this case, it does, because 14.6 is pretty close to 15.4, so it should be close to 100%, and 94.8 is pretty close. And so that is it for Unit 9, which is all about stoichiometry. And in this unit, we learned about how to convert from moles to grams to moles of another substance and all sorts of stuff. And we learned about mole to mole ratios, we learned about percent yield, limiting reactants, and then we also talked about how there's interpreting chemical reactions and finding the number of atoms and all sorts of stuff like that. So if you need any help with any other stuff that we did not talk about in this video about stoichiometry, go back to the other video. And so I hope this helped you learn about limiting reactants and percent yields, and it's always important to set up those conversions correctly and make sure you calculate atomic mass and molar mass all correctly using periodic table. And so that brings us to the end of stoichiometry. And so the next video is going to be all about energy changes and reaction rates. And so we're going to be talking more about reactions. And so until next time, I hope you have a good day, and we'll see you later.